All right, here we go with Chapter 13, Worksheet A. Just going through the assigned problems here. So starting off with number 2. So we're given a cosine function. As typical notation, x is an element of the real number system, which it always is. So that's just kind of common notation. Find the exact value in surd form. That's the IB word for radical. So in radical form of g of pi. So we're just plugging in pi into the g function, and we want to leave our answer in radical form or surd form. So if I were to take that x and replace it with pi, so we'd be looking at 4 pi plus pi over 4 cosine of that, and then times negative 6. One thing you got to be familiar with in this is the unit circle. If we have to put an answer in radical form, calculator is not going to help you with that. So we got to make sure that we understand some of the things with the unit circle and being able to come away with numbers like that. So one thing to keep in mind is that if I have 4 pi sitting here, remember that one time around the unit circle is 2 pi. And if I go another lap around, I'm at 4 pi, and then I go an additional pi fourths. So just keep in mind you can basically ignore this, because if I go pi fourths, or if I go 4 pi plus another pi fourths, I'm still on the same spot, because this repeating yourself to 4 pi is just going to land you, back where you started with if you're on pi fourths. So anyway, so pi fourths, we do need to know the cosine of pi fourths. I should know that as rad 2 over 2, and then I can multiply that answer times negative 6 to get this result. So wanted to show you something you got to be familiar with is the unit circle, at least quadrant 1. Most things that you're given come right out of quadrant 1. If by chance something is given to you that's not in quadrant 1, remember, if you understand how the unit circle works, all you need to understand is that these values continue to repeat all the way around. You'll notice, as you are at pi 6, you can see everything gets mirrored over to the other side, just with a sign change. So as long as you understand how that mirror works from left to right, you see, as you see these values get mirrored over to the other side. If you're going these guys over to the left, well, you're just going to the left instead of to the right, and so your x values change signs, but the y values stayed the same, because I'm still going the same distance up. If you look at these guys as you go from quadrant 1 to quadrant 4, again, notice that these simply get mirrored down to here. The only thing now that changes is the y-coordinate, right? Because instead of going up, you're now going down, but you have all the same values, just with a different sign for the y-coordinate. When you go from here to here, again, everything gets mirrored. The only difference is both coordinates change signs. So now they're both negative instead of both positive, but it's all the same values. So as long as you have some understanding of quadrant 1, you should be able to translate these to any other spot within the unit circle. Anyway, for right now, we're doing the cosine of pi fourths. Remember, the cosine is the x, the sine is your y. So in this case, the x coordinate is rad 2 over 2. So if we go back to, there we go. Go back to the worksheet here. So again, we subbed in a pi right here. And again, we saw how that just repeated us around the circle. So at pi fourths, the cosine of pi fourths is rad 2 over 2. So we sub that in. And now we just simplify. That would become negative 3 rad 2. And again, we left that in surd form or in radical form. Part B, state the max value of the function. Keep in mind, for a cosine function, if you were graphing that cosine function, the parent function starts at 1 and then works its way to look something like this for one full period, but it starts at a value of 1. So when you have a value like this, right, that changes the amplitude. So I'm now doing negative 6 times 1. So now my highest would be 6. My lowest would be negative 6, because remember, this gets repeated. So you're kind of looking at the original parent function max and min right there, but when you multiply those by 6, your lowest now becomes negative 6, and your highest now becomes positive 6. So the max value would go all the way up to positive 6 at its highest. So that would be our max for that guy. Find the smallest value of k for where k is positive, for which this function for all x's that are real numbers. So keep in mind what they're saying right now is here's g of x. and they're basically saying, how would I have to shift this graph horizontally? That's a horizontal shift, so that I would be laying this graph right on top of its original graph. Remember, these graphs continue to repeat forever in both directions, and so if I were to take this and shift it over one period, I would be laying that graph right on top of itself. So all this graph is really asking me is, what is the period of the graph? Because as soon as I do a horizontal shift for one full period, I am then just taking that graph and placing it right on top of itself. So it's just asking me this horizontal shift would have to be one full period in order for the shift to equal the original graph. And so if we just look at the period of the graph, remember we just do 2 pi over b. So in this case, the period equals 2 pi over b. In this case, b is 4, so 2 pi over 4, and we could reduce that to just pi over 2. Moving on. Number 4. So in the triangle ABC, given some values for a, b, and c, find the exact value of the cosine of half of c, and then hence find the exact value of cosine c. There's a couple ways you could do this. Just to keep it simple, I just kind of stick with like a Pythagorean theorem idea. So for this guy, one thing that does matter is if a is 8 and b is 8, that means we are dealing with an isosceles triangle. Knowing those values right here, side c is 12, which means, and since this one's talking about half of c, angle c, when I draw in the altitude, because it's isosceles, I do cut angle C in half, which means I can break up that 12 into 6 and 6. So we've created these two right triangles to the left and to the right. We're going to be working with this guy right here in a second because that would be half of angle C. So in order to do the cosine of that angle, we just simply want to do adjacent over hypotenuse in order to get the cosine of that angle, which is half of angle C. So to get this altitude right here, just a little Pythagorean theorem, 6 squared plus b squared equals 8 squared. So if I kind of do the math on that, 64 minus 36, looks like I get 28. So the square root of 28 is going to be that right there, so it's kind of hard to draw in. Let me do it like this. So the altitude with Pythagorean theorem gives me that look right there. And so now again, just to do the cosine of an angle, we always do adjacent leg over hypotenuse. So rad 28 over 8 would be the cosine of half of angle C. And of course, we can always simplify. You'll notice on this one, it just says the exact value. So as long as I leave it as a radical, I am safe. It did not tell me to simplify, so I'm not required to do that unless the directions specifically tell you to. So you could simplify though, of course. If I clean that up, I could write this. Let's see, that would be 2 rad 7 over 8, which can reduce to just rad 7 over 4. So probably nicer to work with some smaller values, so I kind of like to simplify if possible, but like I said, if the directions don't tell you to, then you don't have to. Hence, meaning now use that answer to find the exact value of the cosine of C. So now we want all of angle C. So a couple ways you could do this, part 2, find the exact value of cosine C. I'm looking in the worked out solutions, and it looks like they used a double angle formula, so I'll just show you where that came from. So here would be the double angle formula that you're seeing in the worked out solution. So that works. You know, we brought in the 2 because originally we had half of C. So if you bring in the 2, now you're looking at the cosine of just C. By bringing in the 2, you're creating the double angle formula. So on the right side, you're going to get this look here, and that works. We don't use double angle formulas a whole lot in this class, so I'm sure a lot of people wouldn't have thought initially to do it that way. We do use the cosine rule, so you know, that's an option as well. If we wanted to use the cosine rule, we could just do it on angle C and just use the cosine rule based on the entire drawing, and that would work too. So use the cosine rule if you want, and that would have worked to get the exact angle or exact value of cosine of C, or you could use the double angle formula. I'm just going to throw that in there and explain it since that's what's in our worked out solutions. So if I had the cosine of half of C, I don't want half of c, I want all of c, so I'm going to bring in the 2 to eliminate the 1/2, and that creates the double angle formula. So then, as I showed you on the other side, we're going to get the cosine squared of a minus the sine squared. Keep in mind, this value right here is what is being placed into these right here. So before the 2 was brought in, I got half c in parentheses right there. So that's the angle I'm working with when I set up the other side, is that half c, which is this angle right here. So this is the one that represents half c. So then when I bring in the formula of cosine squared, it's of half c. So in this case, we knew half of c, or the cosine of half of c, was this value here or this value here. Pick either one. So I'll bring this one in. Minus the sine squared. So in this case, the sine of half of c would have been opposite over hypotenuse, which is 6/8. And so I used this value just so I would have common denominators right here. If I would have used him, I would have had to create common denominators anyway, so save myself a little work by using this version of the answer. So anyway, so that's our setup. A little cleanup on that. If I square both sides, eliminates the radical, so I just get 28/64. 36/64. So now if I subtract, just looking at -8/64, which we could reduce to -1/8. All right, going down to number 6. Number 6, we're given a graph to work with. Here's the general function of the graph. They give us the domain of the graph right here, which we can see it goes all the way to -π/6 to the left, and to π/3 on the right. So they're giving us the domain of the graph. Find the values of a and b. This is simply there to tell us that that graph does not keep on going. It ends at those points, and so we don't try to make any further assumptions about the graph. So just recognize that a has to do with the amplitude of the graph. Remember that in a cosine graph in the parent function would typically start above the midline or above the center. This one starts below, so I know it's negative. And I can see that it goes as low as 7. And so for this graph here, I know the lowest point on that graph is right down here at -7. And I got to use the negative for that guy because it started below the center line instead of above the center line, which means the a value was negative. Do understand the difference between the a value and the amplitude. The amplitude itself is always stated as a positive. So if they were to ask me about the amplitude of the graph, that looks like this, and that would have been 7, because amplitude doesn't have a direction. It goes both up and down, so we always state it as a positive. But if they just ask for the a value itself, that can be negative, so in this case, we got the -7. B has to do with the period of the graph. Remember, for a cosine graph, we know that the period equals 2π/b. And so by looking at this, I can see that this graph repeated itself one full period right here at π/3. So I know that the period of this graph is π/3. And so now I can use that little setup to solve for b. So just solving that equation, I can ditch the pi's and just look at 2/b equals 1/3. So a little cross multiplying here, and I get b is 6. Moving down to number 7. So solve that equation. For x's, all x's between 0 and 360, so that's one full unit circle. Notice it does include 0 and 360 because of the equal signs. That's always something I have to take into account. If that weren't there, those could definitely change my list of values that I list for my solution. So if we are solving for that, so starting to solve here, so cosine squared, one of our identities that we could use. As soon as I see sine squared plus cosine squared, I'd love to. I know that it equals 1, but I can't do that because of the 7, so because he's attached to that cosine squared. So I'm going to replace my cosine squared, knowing the trig identity that sine squared plus cosine squared equals 1. If you rework that identity, then cosine squared equals 1 minus sine squared. Right, so I'm going to do a little substitution here, replace my cosine squared with 1 minus sine squared. So a little substitution there. Now I'm down to just one function, so now I know it's going to be doable from here. Let's distribute. So 7 minus 7 sine squared. So a little algebra here. Subtract the 7. A negative 7 sine squared plus 1 sine squared would equal negative 6 sine squared. So if I just combine like terms, I get the negative 6 sine squared here. I'm subtracting this 7 over to the other side to get that. Divide both sides by negative 6. And now we're back into hopefully familiar territory. So let's see, we're looking at right here. Keep in mind that the sine squared of x is the exact same thing as the sine of x squared. Those mean the same thing, it's just a different way of writing it. So now I can square root both sides and say the sine of x equals plus or minus 1/2 under the radical. Little cleanup on that. Remember, anytime you have a radical like this, we can rationalize the denominator by multiplying like this. And so here's where we get rad 2 over 2. So now if I kind of bring that back in, I got the sine of x equaling plus or minus rad 2 over 2. And so here's where it helps to have some familiarity with your unit circle. So we're saying the sine of what angle equals this result right here of rad 2 over 2. So we know that in quadrant 1, rad 2 over 2 is that 45 degree mark, or pi over 4. So as I start thinking about what should I use, degrees or radians, well, this is my key right here. This is the domain is in degrees, so that means I need to stick with degrees so that I can properly interpret this when I go to state my answer. So as I'm looking at those, remember that I want to keep all x's that are from 0 to 360 inclusive. So I am including 0 and I'm including 360 in that in case that matters. So quick look at the unit circle. So as we're looking at this, so we're saying again the sine of what angle is going to give me either a positive or a negative rad 2 over 2. So we can see right here, remember sine is your y coordinate, and so at 45 degrees, that's a winner right there. If I go across right here at 135 degrees, as I go right here at 225, we can keep him. And as I go right here at 315, we got another winner right there. So for those 4 solutions would make it onto my list because the domain that I'm given, all 4 of those fit within the given domain. So those are the 4 answers I would list. All right, moving on, number 9. Number 9, again, solving another equation. Really important part of this chapter is being able to solve trig equations. A couple ways you could do this. Here's kind of the method you could do just sort of algebraically or by hand. One is to get both of those guys onto the same side. So I'm subtracting the 8 cosine x over. From there, hard to work with if they got the same different functions. So to kind of help separate things out, one thing that you could do to this is divide out the cosine x. And so if I factor out or divide out a cosine x, that becomes 3 sine over cosine, because remember I'm dividing out the cosine x. And that makes him just a 1 right there. So I'm getting this look right here, but that's just a way of separating out the functions so that I can work with it a little more easily. Obviously sine over cosine is tangent, so I can make that conversion. But just like in factoring a quadratic, once you factor it, you set each factor equal to 0 and then solve it. One thing to keep in mind on this though is I just have now created a cosine in the denominator, and you guys know you can never have 0 in the denominator. So one statement I would have to sort of add on to this is just to recognize that the cosine of x can now no longer equal 0 because it's in a denominator. So I have to include that statement just for my own recognition that I can now no longer do this. So now when I go to set my factors equal to 0, typically I would have set this equal to 0 and come up with some solutions for that, because you can do that. But because of what I just did here, that's no longer an option for me. So this factor equaling 0 is no longer an option. I can only set this factor equal to 0. So I'm going to change this to sine over cosine becomes tangent of x. Now if I just start solving this algebraically, add the 8, divide by 3, and we want to know the tangent of what angle is equal to 8/3. So here's where we go to the calculator. I'm looking for an angle, so we use the inverse function. So the inverse tangent of 8/3 gives me 69.4. This one did specifically say round to the nearest degree. Make sure you look for that on the test. If you don't do that, you'll lose a point. So it's a shame to do everything right but lose a point because you didn't follow directions. So round to the nearest degree in this case would be 69 degrees. And then one thing that you should know is from solving equations like this, tangents repeat every 180. So I would also add 180 degrees to this, and I would keep adding 180 as long as I am within the given domain. So if I add 180 to this, I can get another answer. So plus 180. Oops. And there's another answer. So 249 is another answer. If I add 180 again, I'm no longer in the given domain, so I can no longer use that answer. So, but I can use the 249 as another answer because it's within the domain. Just as a side note, if you did set cosine x equal to 0 and solve, and come up with some solutions like that, like 90 degrees and 270 degrees, you would notice if you, like any equation, if you took those answers and plugged them back in, you would also find that they don't fit, they don't work. If I put 90 degrees here and here, or let me go back to the original, if I put 90 here and here, this, if you did it in your calculator, would not equal this, which means it's a what we call an extraneous solution. It doesn't fit if you plug it back in. So you would hopefully then catch it that way if you didn't notice what was going on here. If you just check your answer by plugging it back in, you'll notice whether or not it works. These also work if you plug them back in. If you use 69 and 249, this side is going to be a little different than this side because these are rounded. They're not exact numbers. But if you plug the exact values back in, they would fit. Just a quick idea, if you're watching this, another way to solve an equation like this, it would be to just simply graph. So if I graph the two functions, the 3 sine x and the 8 cosine x, the two from the original equation right there, if I just graph them, take a look at the graphs, you can see there are two solutions. There are 2 points of intersection, one right there and one right there. Those are the two solutions that we came up with for 69 and 249. So those are the only two solutions within the domain that worked. If you ever want help with using this as an option, let me know. I'm happy to go through some of the steps. Just to show you one really quick, once I graph them, if I go under Calc, Second Calc, and choose Intersect, where my cursor is at, there's two, so let's just say I wanted to find this one first, and I hit Enter, Enter, Enter. You'll see down below that at 249 there's one of my answers. I could do the same thing over here and get the 69 as my other answer. So we can use the calculator as well. So moving on, number 14. So determine the exact solutions on this interval. It's really important that you recognize two things about this domain. One is it's in pi, so we're going to do our answer in radians or in terms of pi. The other thing is that it is from 0 to pi inclusive, which means if you get 0 or pi as an answer, you can keep them. Without those equal signs, you could not include 0 or pi, and that's really important to look for when you're doing stuff like this. So we need to know the cosine of what angle gives us a value of rad 3 over 2. So if you look at, let me take you back to real quick to, the unit circle, there it is. So the cosine of what value is rad 3 over 2? Remember, cosine is your x's, so it looks like pi over 6 would work. If you kind of trace that around, where it also has an x value of rad 3 over 2. Looks like right here at 11 pi over 6. So someone might look at this and say, but wait a minute, 11 pi over 6 is not within the given domain from 0 to pi. And I agree, but it's all about what you get at the end, not at the beginning. So I need to start out by setting my parentheses equal to pi 6, set it equal to 11 pi over 6, and we can keep going around this circle forever as many times as it takes to get all the answers, because again, it's not about what you start with, it's about what you end with. So I can include pi over 6, I can include 11 pi over 6. If I keep going, I can also include 2 pi plus pi over 6. I could include 2 pi plus 11 pi over 6. And really I need to test several points to see what all is going to fit in that given domain that we have. So we need to test as much as we can until we start going over pi in our answers, and that's when we kind of know when to stop. So let me take you back to the original problem here for a minute. So again, we did notice that the cosine of pi over 6, 11 pi over 6, and again, I could keep adding 2 pi to that to go further. So I can do any of that stuff plus 2 pi, plus 4 pi, plus 6 pi, and I could keep going all day until I start getting answers that are beyond the given domain. And so keep in mind, we got to test a few points until I run out of room. One mistake that people often make on these is stopping too early, and they don't consider all the options that you could get, because again, they look at this and say, well, I can't use 11 pi over 6 because it's beyond this domain. But again, it's not about what I have right now, it's about what I get after I set this equal to those things and start getting solutions. That's what matters. It's the solutions at the end that matter. So I'm going to start taking my 3x plus pi over 6, and I need to start setting it equal to all of these options and see what we get out of that stuff. So if I set it equal to the first one of pi over 6 and we start solving, so if I were to subtract this, I get 0. Divide by 3 and I get 0. So there's my first solution, and it does fall within my given domain, so I can keep it. And again, that equal sign really matters right now. It tells me whether or not I can keep that answer. If I move on to the next one, 3x plus pi over 6 equals 11 pi over 6. So if I start solving that, so if I subtract pi over 6, I get 3x equals 10 pi over 6. And if I divide that by 3, I get 10 pi over 18. And if I reduce that, 5 pi over 9. And if I do look, that is between 0 and pi, so it's an answer I can keep. As long as I keep getting answers within this domain, I got to keep going. So I'm now over to this guy right here, where I've gone beyond a full circle, but I need to see if I set it equal to this, does it still give me an answer within the domain? If it does, I can keep going. So I'm now looking at my, so let me try to move up a little bit here. If I do my 3x plus pi 6, and set it equal to this, let me see if I can turn that into one fraction. So if I use common denominators, think of this as 12 over 6 plus 1 over 6, so 13 pi over 6. So if I start working from here, subtract 1 pi over 6, I'm now down to 12 pi over 6. If I divide that by 3, I'm looking at 12 pi over 18. And if I reduce that, looks like 2/3, so, so 2 pi over 3. And that is still less than pi, so that's still an answer I need to keep. So it's a good thing I kept going, or I might have missed that answer, and that's a really common issue within this chapter. So make sure you keep testing points until you run out of room within your domain. So 2 pi thirds, that's another one I got to be able to keep. Let me go one more and see if I were to keep going using this guy, do I still get a further answer? So again, let me kind of create a common denominator here. Think of this as 12 pi over 6. So 12 plus 11 is going to give me 23 over 6 pi. So if I, again, set my factor or my parentheses equal to that, if I subtract 1, I got 22 over 6 pi. Divide by 3. And you'll notice on this one, I am now larger than pi, right? That's 22 over 18 is bigger than 1. So I have now gone beyond this domain, so I stop. I can no longer keep that as an answer, and I know I'm done. So again, really important. Add that to the list. Really important that you keep going until you run out of room within the given domain. All right, moving on to 15. I'm switching now back into degrees. Notice the given domains will tell you kind of what to do these in. And so this one says accurate to 1 decimal place, which means I got to use my calculator. And my calculator, according to this, needs to be in degrees. So really important that you notice all those things. Make sure we follow directions to get all the points correct on our test. So solving this equation, looking for everything within the given domain. One thing you'll notice on this, first of all, one step has been done for us. Everything is on the left and it equals 0. Oftentimes, if this guy were on the right, I would need to recognize, kind of like in one that we did earlier, if I can find it really quick. I'm not seeing it, but if you got stuff on two different sides of the equal sign, oftentimes you need to bring everything over onto one side, make it equal 0 so that you can start working with it. So that's something to look for. So now that I'm here, one thing that would stand out to me right away is that both terms contain sine x, so that's something I can divide out or factor out of my function. So I'm going to factor out a sine x. So that now leaves me with all of this. One mistake that people will make is when we say divide out or factor out, you got to keep it. If I were to just go through the equation and divide everything by sine and get rid of sine x, I would be missing out on some answers. So you don't want to lose your x's. You got to keep them involved somehow. So don't divide it out as though it goes away. We factor it out. And so now, like I did on the last problem, I can set each factor equal to 0 and start solving. So if I set my sine x equal to 0, I can get solutions from him. If I set my other factor equal to 0, I can start getting solutions from him. So let's just look at this guy for a minute. So the sine of what angle is equal to 0? So we could do that in our calculator. So if I did an inverse sine of 0 and see what that gives me. So if I do it, and notice I'm in degrees right now because of what we just talked about at the start of this problem. Inverse sine of 0 is 0. So if I start thinking about what values would give me that, 0 is one I can include because it's got the equal sign right here, and so I can include 0 in my answer. If you think about the sign of what values give you 0, right? So right here you got 0 as an option because the y-coordinate is 0. I can also use 180 as another option. Remember, I'm doing this in degrees because the domain was in degrees. So I'm not going to use pi, I'm going to use 180. So 0 and 180 are values I can use. They both give me y-coordinates that are 0. Notice that if I continue to travel around to 360, I can use this point again because 360 was also in my given domain. And so, sorry, there we go. So from this, I should be able to say I get 0, I get 180, I also got 360 according to the given domain that I have right here. So I want you to notice right here as we'd say, uh-oh, this guy does not have an equal sign, so I cannot include him in my answer. And so that's really important that you notice what has an equal sign and what doesn't, so you know what to keep and what not to keep. And so I'm only going to keep the 0 and the 180 based on him. If I look over here, I'm going to just bring my 1/5 over. Multiply both sides by 4. And again, do the inverse cosine of 4/5. So if I go into here, my inverse cosine of 4/5 gives me about 36.9. Remember the directions said 1 decimal place, so 36.9 would be the most appropriate. And as we consider other possible solutions from that, here's the best way to kind of view what your other possible answer might be for this. If I look at the unit circle for a minute, take you back there if I can find it. There we go. Keep in mind what cosines do. Remember, cosine is the x-coordinate, so it has to do with left and right. If I look at this, notice the cosine of this angle, 30 degrees, is rad 3 over 2. If I'm also going to the right, then I also have a matching cosine answer right here at 330 degrees, right? Because both of these are going to the right, I get the same cosine value. So if I were to travel 30 degrees in terms of cosines, that is the same thing as going 30 degrees this way to get my other answer for that one. So do the same thing with what we have right now. I have 36.9 degrees, so to go 36.9 degrees this way would get me the same cosine result as if I were to go 36.9 degrees this way. And so for my other answer, I need to do 360 minus 36.9 to get my other answer. And so if we do that algebraically, I need to do 360 minus 36.9 to get my other answer. And so 323.1 should be my other answer. And I think we got some wrong answers written in the worked out solutions, but as I just showed you, this is what would make sense. And those answers, both of those fit within our given domain of 0 to 360, so I should be good with these 4 answers. All right, moving on. Number 18, 2 more. So number 18, so we got 2 functions for f and g. There we go. So f, we got tangent of x, we're given a domain for that. And then g, we're given this guy, and we're told that x can be any real number. So now we're solving this equation. So we start out by plugging the f function into the g function. So I am taking the tangent of x and plugging it into that x right there. So it should say tan x times the square root of 3 minus 1. So we got the tangent of x times the square root of 3 minus 1 equaling 0. So we're just setting it equal to 0 based on that. So there's our setup right there, and now we just have to solve the equation. So if we just started solving this, we'd add over the 1, divide by the square root of 3, and we're looking at the tangent of x equaling 1 over the square root of 3. And then we like to rationalize that denominator. We don't like the radical on bottom, so we multiply by rad 3 over rad 3 to clear that out. So we are looking at the tangent of x equaling rad 3 over 3. And so similar to what we've seen before, we just now need to kind of understand from the unit circle what angle would give me the result of rad 3 over rad 3 over 3. So if we go to our unit circle for a minute, keep that image in mind here, rad 3 over 3 for tangent. So if we pull up our unit circle, so remember for tangent is sine over cosine, so we are doing y over x, and the result should be rad 3 over 3. Oops, let me go back to that. So if we look at pi over 6, if I were to do y divided by x, we would see that the result is rad 3 over 3. So my first result would be pi over 6. If you look at the domain for this problem, it's given in terms of pi, so I do need to answer in radians. However, if you have a hard time figuring out where the first value should be, one thing you could kind of take advantage of on the calculator is in a case like this, I could easily do it in degrees first. If I do the inverse, according to this, if I did the inverse tangent of rad 3 over 3, I get 30 degrees as my answer. So all I need to do is basically convert 30 into radians, which is by multiplying it times pi over 180, and that would give me pi over 6. And so that's kind of an easy way I could take advantage of my calculator to get my answer of pi over 6. So, because otherwise you might have a hard time figuring out by doing y divided by x where this would come from. So that's something you could take advantage of. And then to kind of finish it off, to get any other answer, tangents repeat every 180 degrees. So this answer here, and you just take a look, you'll see where it comes from. If I did this divided by this, as I travel 180 degrees, right, I get the same result out of this. They're both negative, so it's going to come out to be positive, just like this one did. So if I travel that 180 degrees, 7 pi over 6 would be my next answer. If I traveled another 180 degrees, I would go past my given domain. So I'd have to stop with those first two answers of pi over 6 and 7 pi over 6. All right, let's go back to this. All right, moving on to the last one, number 20. Find the exact solution. So just solving another equation for this. It's obviously something we got to be able to do this chapter. All right, so for this one, so one thing that should stand out to you right away is that you have a double angle right here. So that 2x, definitely something we can convert. So let me just bring over first my cosine of x, which is pretty normal. You pretty much typically are going to want everything onto one side, make the whole thing equal 0, so that we can kind of create some kind of a setup with factors or something like that and set them equal to 0. So for this one, we want to convert our double angle formula. These are all in your formula packet, so if you ever run into something like this, check the formula packet for where to go next. But if I look at the sine of 2x, using a double angle formula, the sine of 2x is equal to 2 sine x cosine x. So I can replace that. So 2 sine x cosine x. And that puts me here. Obviously the 1/2 and the 2 can cancel each other out. So those guys are gone. This is the point where you should recognize that because there's a cosine in each term, I can now factor out the cosine of x. Remember, you never want to divide it by the whole thing and get rid of it. You want to simply divide it out or factor it out and keep it, because we need to get an answer from him. If we divide the whole equation by cosine x and that cosine goes away, we would miss out on some solutions by doing that. So we want to keep it involved by factoring it out. So now we're here, and just like what we've done before, once you get your factors, you set each factor equal to 0, and we get our solutions from those. If I set this equal to 0, I'll end up adding the 1 over. So let me just do that step now. So this is where we need to get our answers from. So make sure we follow directions. I do need exact solutions, and according to this, I want them to be in terms of pi or radians. So because of what I see right here, it is from 0 to 2 pi inclusive because of the equal signs. So if we consider the cosine of what angle gives us a 0, remember the cosines are like your x's. So if you think in terms of the unit circle, the cosine of what angle would give you a 0? So where are the x's 0? So right here at pi over 2, and right here at 3 pi over 2 is where we can get those first couple answers. So for the first one, and then for the other guy, the sine of what angle gives you a value of 1. Remember, the sine is your y value, so the y values that have a 1 on them are only this answer right here at pi over 2, but we've already recorded that answer. So those are the only two answers we're going to come up with. And that's it for worksheet A.